Hello students, I welcome you in today's session of physics. As in physics, we are discussing a topic rotational motion and moment of inertia. As you know very well, in our previous lecture, which is lecture number 1, we had covered out the moment of inertia. Clear? Most of its topic you can see here, the radius of gyration. These are the things we had already covered out. Now today we will discuss about, this is the lecture number 2, and here in today's class we are going to discuss the theorem of parallel and perpendicular axis. You can see here, this is the thing we are going to discuss right now. So what is the theorem of parallel axis? So this theorem states that the moment of inertia, which is I, of a body about any axis is equal to the moment of inertia ICM about a parallel axis through its center of mass plus the product of the masses m of the body and the square of the perpendicular distance a between the two axes. So you can write it like this: I is equals to ICM plus MA square. Now we have to prove this relation using this figure. You can see here, with the help of this figure we are going to derive the expression for the theorem of parallel axis. So you can see here a C point given with the center of mass of a plane lamina. You can see here, this is the plane lamina. Let I be its moment of inertia about an axis AB in its plane. Clear? And ICM be the moment of inertia about parallel axis, which is your EF. This is about moment of a plane axis and this is the parallel axis passing through the C. So let the distance between EF and AB be how much? Small a. You can see it. So let us consider a particle P of mass small m at a distance small r from EF. Its distance from AB is how much? R plus A. Fine. And its moment of inertia about it is mr plus A square. Therefore, the moment of inertia of the lamina about AB is given by, you can use this expression like this: I is equals to sigma m RA plus A whole square. Clear? And if you open the whole square, you know it very well, A plus B ka whole square, A square plus B square plus 2AB. So from that we write this relation like this. You can also write like m r square plus m sigma m a square plus 2 sigma 2 m a r. Since A is a constant, so it can be taken outside, and the relation comes looks like this: I is equals to summation of mr square plus A square summation of m plus 2a summation of mr. Clear? Now you can see here, summation of mr square is equals to ICM, and ICM is the moment of inertia of the lamina about EF. Fine. And what is A square summation of m? Is equals to A square m, where m is the total mass of the lamina, and summation of mr equals to 0 because the sum of the moment of all the mass particles of a body about the axis through the center of mass of the body is 0. Hence, making the substitution in equation 1, we finally get like equation in this form: I is equals to ICM plus MA square. This is your theorem of parallel axis. These two theorems are very important, so read it properly. Now the second one, come to the second one, theorem of perpendicular axis. So this theorem states that the moment of inertia of a uniform plane lamina about an axis perpendicular to the plane, you can see here, plane lamina about an axis perpendicular to its plane is equal to the sum of its moment of inertia about any two mutually perpendicular axes in its plane intersecting the first axis. You can see here this theorem we can prove here from this figure. So let us suppose, you can see here, OZ axis be the axis perpendicular to the plane of lamina about which the moment of inertia is to be taken. You have to find out the moment of inertia about this axis. Let OX and OY be the two mutually perpendicular axes in the plane of lamina and intersecting the OZ. Clear? So let us consider a particle P of mass small m at a distance small r from OZ. The moment of inertia of this particle about OZ is how much? Mr square. Therefore, the moment of inertia of the whole lamina is OZ is Iz is equals to summation of mr square. Clear? This one. But you know very well, r square is equals to x square plus y square. From this figure, you can, if you want to find out the value of r, then it comes out to be r square is equals to x square plus y square, where x and y are the distances of P from OY and OX respectively. Clear? So Iz, if we write the equation, it changes like Iz is equals to summation of mx square plus y square. In place of r square, from this equation we put x square plus y square, or you can individually separate them. So summation of mx square plus my square, but summation of mx square is the moment of inertia, Iy of the lamina about Oy, and summation of my square is the moment of inertia, which is your Ix of the lamina about Ox. So finally, if you combine both of them, we get the moment of inertia about the z axis, which is Iz is equals to Iy plus Ix. I hope it is clear. Now here you can see there are the some formula for the moment of inertia of certain regular bodies. It is given here. Fine. So what are the regular bodies? I am not going into the deep. I am just telling you, you have to understand the formula. Moment of inertia of a rod or a thin bar. You have to remember these formulas because it can be asked in your examination. So what is the moment of inertia of a rod? So ICM, center of mass, is equals to ml square, with L is the length, by 12. This is the moment of inertia for a thin rod. Or about an axis perpendicular to the end and passing through one end of the rod. In that case, what is the moment of inertia? It changes to I equals to ml square by 3. Clear? Kindly remember these formulas. Moment of inertia of a rectangular lamina or plane. In that case, the moment of inertia, it looks like this: I equals to m l square plus b square by 12. This is for the lamina. Third one is the moment of inertia of a ring. Now there are the two cases: an axis passing through center and perpendicular to its plane. Then what happens? Moment of inertia is equals to IMR square. And if we take moment of inertia about its diameter, then it is written like ID is equals to half mr square. This one. Clear? Now the fourth one, moment of inertia of a circular disc. This one. So about an axis passing through the center perpendicular to its plane, so its moment of inertia I equals to half mr square. Kindly remember this formula because they are very important from the examination point of view. Similarly, the moment of inertia of a solid cylinder, it can be written like this: I equals to m l square by 12 plus h square by 4. Moment of inertia of a hollow cylinder is I equals to half m r square plus r square, where r is the radius, outer radius, and small r is the inner radius. Clear? There is another case in the cylindrical, an axis passing through its center and mass perpendicular to its length. Then what happened? Inertia is equals to I equals to m l square by 12 plus r square plus small r square by 4. Same thing given here. Moment of inertia of a solid sphere, you can also remember this: I equals to 2 by 5 mr square. And if we measure the inertia about its tangent like this, so what happened? Then its moment of inertia equals to tangential inertia 7 by 5 mr square. Moment of inertia of a hollow sphere about its diameter, you have to know this formula: 2 by 5m r to the power 5 minus small r to the power 5, and same thing denominator. Moment of inertia of a spherical cell about its diameter, this comes out to be I equals to 2 by 3 mr square. So these are some formulas. Kindly remember all these. Fine. Now we will come to relation between torque and moment of inertia. This one. Clear? Suppose a body acted upon by a torque tau is rotating about an axis passing through a fixed point O. Clear? So let it have a constant angular acceleration alpha. So the angular acceleration of the particles of the body will be the same, which is your alpha, but the linear acceleration will be different. Suppose the mass of one particle of the body is a small one and its distance from the axis of rotation is r1. Then the linear acceleration of the particle is a1 equals to r1 alpha. Clear? So if we suppose here ki F1 with the force acting on the particle, then F1 equals to how much? Mass into acceleration m1a1. In place of a1, you can write from this formula r1 alpha. So this is changes to m1 r1 alpha. Moment of inertia of this force about the axis of rotation passing through O is how much? You know it very well. Force is into distance. Clear? Tau equals to F into D. So in place of force, you put this relation, and in place of R1, you put R1. So it changes into M1 R1 square multiplied by alpha. Similarly, if the masses of other particles be m1, m2, m3 and their respective distances from the axis of rotation be r2, r3, then we can write it like this respectively. So the torque acting on the whole body will be the sum of the torque acting on all the particles. So this changes to in this form, tau is equals to m1 r1 square plus m2 r2 square plus m3 r3 square and so on, and multiply by alpha. So finally you can summation of mr square multiply by alpha. Clear? But mr square is the moment of inertia I of the body about the axis of rotation. So you can write it like this, tau is equals to I multiply by alpha. Yani torque is equals to moment of inertia into its angular acceleration. Clear? So if in the above equation we take here alpha equals to 1 and I equals to tau, so the moment of inertia of a body about an axis is equal to the torque required to produce the angular acceleration in the body about that axis. I hope it is clear. Now we will come to, you can see here, I am not getting in the detail of kinetic energy of rotation. Here we are going to discuss right now relation between angular momentum and moment of inertia. The topic number 12. You can see here. So what happens when a body moves along a straight line, then the product of mass and the linear velocity, which is your small v, okay, of the body is called its linear momentum. You know it very well. If a body is rotating about an axis, then what happen? The sum of the moments of the linear momenta of all the particles about the given axis is called the angular momentum of the body about that axis. It is represented by a small or j, capital J, you can represent it. Let a body be rotating about an axis with the angular velocity omega. So all the particles of the body will have the same angular velocity, but the linear velocity will be different. So let a particle be at a distance small r1 from the axis of rotation, then the linear velocity of this particle is given by v1 is equals to r1 omega. Clear? If the mass of the particle we take here m1, then its linear momentum is m1 v1. The moment of this momentum about the axis of rotation, momentum into distance. So we finally find out here after putting all the values, m1 r1 square multiplied by omega. Similarly, if the mass of the other particles be m2, m3 and so on, and their respective distances from the axis of rotation be r2, r3, then the moment of the linear momenta about the axis of rotation will be m2 r2 square omega, m3 r3 square omega respectively. The sum of the moments of mean linear momenta of all the particles, that is the angular momentum of the body, is given by using this formula. You can see here. But summation of mr square is the moment of inertia I of the body about the axis of rotation. Hence the angular momentum of the body about the axis of rotation is equals to j is equals to I omega. The SI unit of angular momentum is kg meter square per second or joule per second. This is the unit of angular momentum. And dimension formula we talk about, so ml square t minus 1. Clear? Fine. Now the same thing we have to set up a relation between the torque and the rate of change of angular momentum. Clear? You can see here this one we have to discuss now. Suppose a body is rotating about an axis under the action of a torque tau, and its angular acceleration is how much? Alpha. So you can write it this relation like tau is equals to 1 multiplied by alpha, where I is the momentum of inertia of the body about the axis of rotation. Now you know very well alpha equals to dy by dt, that is rate of change of angular velocity. So in place of alpha you can write it tau is equals to I d omega by dt. The angular momentum of the body about the axis of rotation is j is equals to I omega. So this relation changes to j is equals to I omega. And finally, if we differentiate it with respect to the time, so dj by dt is equals to I times d omega by dt. Clear? Hence from equation 1, this is your equation 1, you can see here this one, the relation with the torque, this one. So from this equation we can write it in place of I d omega dt, we can write torque. So dj over dt is equals to how much? Tau. That is the rate of change of angular momentum of a body is equal to the external torque acting upon the body. Clear? Hence from equation 1 this is your equation 1, you can see here this one, the relation with the torque, this one. So from this equation we can write it in place of I d omega dt, we can write torque. So dj over dt is equals to how much? Tau. That is the rate of change of angular momentum of a body is equal to the external torque acting upon the body. Clear? Fine. Now we will have to discuss the linear, or you can see here, conservation of angular momentum. These things we are not going to the deep. Now we will discuss in our next lecture about couple. Clear, students? Okay, that's all for this today's class. Thank you, students.